Hi everyone, my name is Muhammad Shakifah and today I'll present to you about the summary of four research papers related to recent advancements in computer architecture. So the first paper that I review is about the MLIR, a compiler infrastructure for the end of Moore's Law. It introduces the MLIR, a flexible compiler system supporting multiple levels of abstraction. It helps to unify optimization and also support integration with existing systems like TensorFlow and also LLVM, making it easier to target a new hardware. While promising, the paper could better address adoption challenges and also user learning curves. So for the next paper that I reviewed is about a survey on coarse-grained reconfigurable architectures. This paper reviewed 30 years of CGRE research and explained design classification. It is valuable for new researchers to understand performance trade-off. However, it lacks detailed runtime analysis and also benchmarking that would make it more practical. So the third paper is about the advancements in microprocessor architecture for ubiquitous AI tracks the evolution from CPUs to GPUs and also MPUs for AI workloads. It highlights the need for optimization in memory and also parallelism. While insightful, it will be more beneficial for more technical depth and also real-world benchmark. And last but not least, I look at a paper on RISCV, vector extensions for image processing. It demonstrates a custom accelerator and a lightweight neural network that runs efficiently on RISCV. It is great for HAI, but comparison with other accelerator would strengthen its claim. And for the key insight of this research paper is how modern computer demands, especially AI and hardware diversity, are shaping the architecture landscape. Innovation in modular compilers, flexible hardware like CGRAs and also RSCV, and also evolving microprocessor design are driving the future. Thank you.
This slide shows the simulation results for two datasets, CESP on the left and EAR on the right. Both experiments analyze how cache size affect the miss rates using a fully associative cache configuration. Starting with CESP, we can observe a very sharp decrease in miss rate as the cache size increase. At just 0.032 kilobyte, the miss rate is high around 52.92%, which indicates frequent cache misses. But as the cache size increased to 0.512 kilobyte, the miss rate dropped significantly to just 1.54%. And then levels of around 0.74% from 4 kilobytes onwards. This suggests that after a certain point, increasing the cache size offers minimal benefit as most of the working set is already stored in the cache. Now, let's look at EAR. The trend here is similar. Although the drop is more gradual, it starts at 59.95% miss rate at 0.032 kilobytes and decreased to 18.22% at 0.512 kilobytes. The improvement continues until it stabilizes at 6.71% from 8 kilobytes onwards. This again shows that larger cache reduce miss rate, but only up to a point where the cache becomes large enough to handle most memory requests. In both datasets, we see a clear demonstration of the principle of diminishing returns in cache performance. Initially, increasing cache size significantly reduced miss rates by minimizing capacity misses. However, beyond a certain size around 4 kilobytes to 8 kilobytes, the gains become minimal, indicating that the cache already fits the working sets.
Hi everyone, I will explain how cache size affects miss rate today. So in the chart we see that as cache size increases, the miss rate drops sharply, especially from 0.03 kb to 4 kb. This is because a larger cache holds more data, reducing the need to fetch from slower memory. The drop in miss rate is mostly due to fewer capacity misses, and since this is a fully associative cache, there is no conflict misses. Compulsory misses don't improve much, and there is no coherence misses here. Um, also we see that at certain sizes the miss rate drops suddenly. That's when the cache becomes big enough to store the full working set. But after a point, increasing the cache size brings little benefit. Let's call this diminishing returns. In short, bigger caches reduce miss rate, but only up to a certain limit. Thanks.
Hi, my name is Ilham Alif bin Muhammad Shukri, and in this section, I'll be explaining how we use Git and GitHub as our version control system for the TAO6123 project. Let's start with the basics. Version control is essential for any collaborative software project. It helps us track every change, coordinate teamwork, and maintain a complete history of our codebase. For our project, we created a GitHub repository, invited all team members, and set up a shared file called member.txt. Each member added their name and committed their changes, allowing everyone to see who contributed and when. This simple workflow, cloning the repository, editing files, committing changes, and pushing updates, ensured that our progress was transparent and that everyone stayed in sync. Next, I'm going to discuss about the transformative impact of Git and GitHub. These are tools that have revolutionized version control and collaboration. It is created by Linus Torvalds in 2005 to address limitations of earlier systems like BitKeeper. Git was designed to support distributed development with a focus on speed and data integrity. Remarkably, its working prototype was completed in just 10 days. Over time, under Junior Hamano's stewardship, Git evolved with advanced features like branching workflows, enhanced collaborative capabilities, becoming a powerful general-purpose tool. Git's distributed architecture allows developers to work offline with a full local repository, while features like SHA-1 hashing ensure data integrity and delta encoding optimizes storage. While Git is a local version control tool offering capabilities like committing changes and managing branches, GitHub complements Git by providing an online platform for hosting repositories and enabling collaboration through tools like pull requests, issue tracking, and CI or CD workflows. Together, Git and GitHub form the backbone of modern collaborative development. Git shines in supporting flexible workflows, robust branching, and in-depth code reviews, while GitHub provides centralized access for seamless teamwork. For assembly language or mixed language projects, these tools make management, tracking, and integration easier while ensuring technical adaptability. To conclude, the evolution of Git and GitHub has fundamentally changed how individuals and teams approach development projects, enabling both individual efficiency and scalable collaboration. By embracing these tools, developers gain the ability to manage complexity while fostering better teamwork. Thank you for joining this discussion on the innovations in version control. Thank you.